Alright guys, today we're going to be looking at yet another problem. I'm calling it the truck capacity, and we'll be using binary search to solve this problem. But first let's try to understand what the problem is and what insights can we derive from it, and see why our intuition tells us to use binary search in this case, right? And so let's dive right in. The goal here is, the problem statement here is, given a list of weights and the number of days, find the minimum truck capacity required to deliver all packages within D days. So, so looking at the problem statement alone gives me a clue, and the clue is that this is a minimization kind of problem because I'm looking to find the minimum truck capacity required, right? And I have got a list of weights, which would be the list of items or the packages that I want to deliver. Let's call it packages going forward. So I have added an example here. Let's say we are given a list of weights, right? This is the first package which weighs 1 pound. This is the second package which weighs 2 pounds. This is the third package which weighs 3 pounds, and so on. And we have D equals 5, which signifies we have 5 days to deliver all of these packages. Now, one assumption that we can make in this question is that we only have one truck to deliver all of these packages, right? But we are given multiple days to deliver them. We need to find the minimum weight capacity of our truck that's required to deliver all of these packages within 5 days, right? So let's see. Our assumption is we only have one truck, right? And our assumption is we have 5 days to deliver. But let's say we only had 1 day to deliver, and the capacity was, well, only 1 pound. Would we be able to deliver all of these packages? Well, logically, we'll never be able to deliver all of these packages because you see the truck capacity is 1 pound, and the first package itself weighs 1 pound. And so on day one, we'll only be able to deliver the first package, and we'll have to leave out all these packages, and that won't serve our purpose. And so we can either increase the number of days or the number of the capacity of the truck, but the number of truck remains the same, which is 1. So we have two things that we can play with, and we are already given that we can take 5 full days to deliver. So there's no point trying to increment the number of days because we're given that we can use 5 full days to deliver, and so that's not a varying number. We can set it to 5 directly. So let's set it to 5 days, and let's get rid of all of these other cases. We have one truck, 5 days. What would be the capacity of the truck that would allow us to deliver all of these weights? Logically, I could say the capacity of the truck could be 100 pounds, right? Which would mean that could fit any package in this list, and that would allow us to kind of deliver all of these packages on day one. But since we need to minimize this capacity of our truck and utilize all these days, it would be naive to just say that let our capacity be 100 pounds. We need something way smaller than this, right? Because it will be waste of space and waste of capacity, because we'll never be utilizing full 100 pounds of our capacity even if we deliver all of these packages at once, right? And so one way to look at it is, let's start at some greater number, in this case 100 pounds, and let's see if we can shrink it by half, right? Let's say, okay, 100 pounds is too naive, we are wasting a lot of capacity, let's do 50. Okay, sounds good. So 50 on day one, right? So let's start writing it like this. Day one, what will we be able to deliver? What all packages will we be able to deliver? Which is 1 plus 2 3 plus 3 6 plus 4 10 plus 5 15 plus 6 21. We got 28, 36, 45. Well, we'll be able to deliver all the packages until this package. So we'll be able to deliver all the packages but one. So how many packages do we have? Let me see. We have 10 packages, so we'll be able to deliver 9 of them but one. So on day 2, we can easily deliver the remaining package, right? which is one package, the very last package. We can deliver 9 packages. We can deliver one package at the very end, which is the package that weighs 10 pounds. Now you see, we haven't utilized day 3, we haven't utilized day 4, we haven't utilized day 5, which means we still have scope to reduce this number. Now let's shrink it. I would say let's again shrink it by 25, right? So let's shrink it to 25, which is shrinking it by half, and let's see how many packages we will be able to deliver on day 1. So again, on day 1 we would be able to deliver, we already have 9 plus, we already have one package, 2, 3, so that's 3 plus 3 6, we have 10, 15, that's 21. That's about it, right? We'll be able to deliver packages from 1 to 6. So we'll be able to deliver packages from 1 to 6 on day 1, right? 1 to 6 packages on day 1, and we are left with 4 more packages to deliver, right? And so on day 2 we'll be able to deliver 7 plus 8 plus 9. Will we be able to deliver all of these? Yes, we will be able to deliver all of these. And you see, by day 3 we'll be able to deliver all of these packages, right? Which is 7 to 8, and then we say, oh sorry, 7 to 9, and then we say 10th package, and that's about it. We are still not utilizing these days, so we can shrink it by half again. So let's shrink it by half. So again, if we shrink it by half, we're gonna get 12.5 or something. So let's round it off and say let's just say 15, right? Let's just shrink it further. 15. Okay, sounds good. 15 pounds. Now let's see, 15 pound. We have on day 1. What all can we deliver on day 1? Let's reset all of our days. We have 1 truck on day 1, and we have for truck capacity 15 pounds. Let's see what packages can we deliver. We can deliver the first package for sure. 1 plus 2 3 plus 3 6 plus 4 10 plus 5 15, and that's about it. We have reached our maximum truck capacity so far, which is 15 pounds. So we can deliver packages 1 through 5, right? And on day 2 we'll be able to deliver 6, right, plus 7, that's 13, plus 8, that gives us 21. So that exceeds our capacity, so we can only deliver packages 6 and 7. Packages 6 to 7 can be delivered on day 2. On day 3, let's look at day 3. Day 3, 8, 9, 8 and 9 alone, right? So packages 8 to 9 on day 4, 10th package. Okay, can we shrink it any further? That's the question. The capacity that we have reached is 15 pounds so far. We have been shrinking it. We started at 50. We shrunk it once, twice, thrice, 3 times, and shrunk it by half every time. And we have 15 pounds right now. Can we shrink it any further? Can we bring it down to a lower number? Let's see. Let's say if it was 10. The problem with 10 here is that we won't be able to deliver the last set of packages. You can see how. You can walk through the example and see how, but I have done it before, so I know that with 10 pounds we'll have the 9 and 10 remaining after day 5, or we'll at least have the 10th package remaining after we have delivered on all of these days. And so 10 is not going to work, 12 is not going to work as well, 13 is not going to work, 14. You can walk through these examples again to see, but I would say only 15 works. And so as you can see, we tried to utilize all these days as much as possible to deliver all of these packages, but eventually we need to find the minimum capacity, and we found it to be 15. And so the output is 15. That's the right answer here. Okay, now that we have walked through the example and understood what we need to do and how we are trying to minimize the truck capacity here, let's see what our intuition was. We started out with a huge arbitrary number. We said, okay, let it be 100, right? That kind of made us shrink this capacity 3 to 4 times. But what if we started with a lower number, right? And logically speaking, we are already given the weight list. And so we don't have to pick a random arbitrary number as our initial capacity. We can look at our list and define our search space for the capacity, right? So the minimum capacity here of our truck should at least be 10 pounds, right? That's the pause I gave so that you can think about it. But it should be 10 pounds, and the reason is the heaviest package here is 10 pounds, and our truck should at least be able to carry one package at a time. And so the heaviest package should be the minimum capacity of our truck. And what should be the maximum capacity of the truck? Well, the maximum capacity could be anything, right? It could be infinity. It could be 10,000, 20,000. But in this case, the maximum capacity should be that we are able to deliver all of these packages on a single day. We don't care about the number of days. So if I say I don't care about the number of days, I want to deliver all of these packages on day 1, my maximum capacity of truck should be nothing but sum of all these weights, right? And now I have defined kind of this search space for myself. I've said that my golden number that I'm looking for, which is the minimum truck capacity, lies between 10 and in the sum of weights. Okay, and now that I have defined my search space, something quickly struck me, and that is that I can use something called as binary search that I have already been doing so far for other problems where I had to shrink my search space by half every time. I would be able to reach my minimum truck capacity golden number in half the time, or in log n time, right? And that is the ultimate intuition behind using binary search for this problem, because we were successfully able to come up with a search space for ourselves. And then once we have our search space, we know that we need to find our number, and we are sure that our number lies between this minimum and the maximum capacity that we have set for ourselves. So let's quickly write a class. Okay. Let's call it truck capacity, and that class should let's say we have weights, and then what would we initialize? We initialize the days, and that's about it. Those are the two things given to us. Weights is weights, and then this dot days is equal to days. All right, and so let's also say that we are given weights. My bad. Yeah, and then let's define our methods. First function would be our minimum capacity, right? And it needs to return something. Well, it can return a lot of things. Now, as you notice here, the function should go away, the function keyword, because within a class in JavaScript, the way to define a function is just to name it and then have an open parenthesis and close parenthesis after it. This would mean that we are defining a function, right? And this needs to return something here, okay? And so let's look at our goal again, and the goal is to find the minimum capacity of our truck, right? And so let's start writing what we already had thought about, which is setting our bounds. So first thing, let's try to set our bounds, right? So our bounds would be minimum, I would say minimum left bound will be max of weights, and the right bound will be the sum of math dot, oh my bad, sum of weights, right? So we have got our left bound, we have got our right bound, and as a good practice, let both of them be the variables that would be used only in this function's scope. And then once we have this, as we said, we're going to start from the left bound and we're going to go to the right until the right bound, and every time we're going to look for a middle point, and so our mid is going to be left bound plus right bound over 2. Alright, that gives us mid. And now at this point we have got our mid, and now we need to go through our weights to check if this number would work. Let's call it potential truck capacity. We need to test this potential truck capacity, right? Check if we can deliver all packages using this truck capacity in D days, right? And so instead of doing all that check here, let's create another function to do it. Say if it is feasible to do it, right? Is it feasible to do it? And let's say it takes in capacity as the parameter, and then we say that the let's say we say days, let's say required days, let's initialize it to 1, okay, and we need to, let's also have a iterator set to 0 to iterate through our weights array, and we can say while I is less than, say this dot weights dot length right, and this dot weights dot length, we're just iterating through it. In each iteration we have to do I++, and then finally we'll be checking if our weights of I, which would be the package weight, is less than or equal to the capacity that's given to us here. If it is less than or equal to the capacity, then we can easily use our capacity to carry that package, weights I, and then move on to our second iteration. If that's not the case, then we have a problem. Then we need to move to the second day, right? If we have reached the capacity for our day, then we need to move on to the second day. So we increment the required days, and then we say capacity is equal to the original capacity. Now that we have been decrementing it, we say we have to store capacity somewhere, right? So we store it in the original capacity, and then we reset our capacity to the original capacity for the second day, and so on. Now at any given point, and so this should return if it is feasible, right? If it is possible, return if it is possible to deliver all packages within given a capacity of a truck. So quite easily we should be able to say that if required days is less than equal to the days that was originally given to us, then we were able to deliver all of these packages using this capacity, right? Okay, sounds good. And now let's go back to our main function, which would be called externally, which would be the main interface here. We would say that we need to do the feasibility check once we have found the potential truck capacity, which is nothing but the midpoint of the left and right bound. Okay, so if feasible, we called feasible here, and we passed in our potential truck capacity to it. And now if it is feasible, then all we just do is try to shrink our right bound further. Now one more thing to note here is, since we are shrinking our right bound, we need to store our result somewhere, right? So let's store our result somewhere. Result is initially right bound, the maximum weight, maximum capacity. Now as we shrink our right bound, because it's feasible, now we want to look for a smaller value which we can use to deliver all these packages, because remember our goal is to minimize the weight. So our right bound is going to be equal to potential truck capacity, which is this one right here, minus 1, right? If it is not feasible, then we need to set our right and left, then we need to say, okay, we need more space, so we say our left bound is potential truck capacity plus 1. Alright, so before shrinking the right bound, we know that the last weight that allowed us to deliver all of these packages was the potential truck capacity. And once we stored the potential truck capacity here, we're just going to go back and do the iteration again, and eventually we're just going to return result. Simple binary search here, nothing out of the normal. Okay, all right. Now that we have some set of functions defined for us, let's try to call it, right? All right, so let's say our JavaScript module is going to call this, right? And let's create a truck capacity object to find out our truck capacity. So we capacity equals new truck capacity. That's the new class object, and then we need to pass in weights, and so let's also have weights, and then let's also have days defined. Let's have 5 days here in our example, and then we say weights, and then we pass in days. That's all our constructor takes as parameters. and then 5 is the days, and then let's copy the wait list from our example here, and then okay, got it right here. Then we pass it in. Now that we have initialized, we just need to print capacity dot minimum capacity. Okay guys, now that we have called our function here, let's go back to do a one final validation check to see if everything is correct. So I added a couple of code snippets here. So in our constructor, when we initialize weights and days, I created a small for each loop to calculate the sum of weights that we can in turn use as a right bound right here in the function. And then we have also done the math.max here, but we would need to use a list of integers and not a array in JavaScript. So this is a spread out operator, and this is used to spread out the elements of this array. And so this would kind of give us something like this: 1, 2, 3, and so on. Okay, and now that we have our left bound and right bound, we need to do one more thing here. In JavaScript, this would give us decimal division. We need math.floor to get the integer value. All right. So once we get the potential truck capacity, everything else looks good. If it is feasible, then we try to shrink it. If it's not feasible, we try to increase it. All right. Now let's run this code online. Okay. All right. So this is our code. Let's try to run it online. I use programmers.com. It's a good way to run it. It uses Node.js to run it behind the scenes, and we have got 15 for the example. All right. So this was a very simple problem, and this was simple in the sense that we already knew binary search. If we wouldn't have understood binary search completely by now, we would be stranded somewhere trying to find the minimum truck capacity by going through the array and trying to use DP, dynamic programming, and whatnot. But it's a very simple problem, and then we can go back to our problem and define the time and space complexity here. The time and space for this is again, the time required for this is like an n log n, and the reason is n is, now there are two things here, n log k, let's call it k, where n is where k is the left bound minus right bound, right? So right bound minus left bound, and then n is number of weights, or the length of weight array. And yeah, that's about it. Well, we'll see you in the next one with a new question, and happy coding, guys.